Yeah, thank you very much for your invitation to give the talk in this series. Those who know me probably know that I have been working mostly in condensed matter physics or squalid state physics recently. And this is my first talks for in a long time on nuclear or this unclear in quote physics. The talk is based on a recent paper that that Hans Hammer and myself have posted on the internet last month. We are still thinking about different future directions, so any comments that you might have would be welcome. So in short, a very short summary would be that what we call an unnucleus in this talk is a field in a non-relativistic conformal field theory, and I will spend some time explaining in gross features what we need to know about non-relativistic conformal field theory to do basically phenomenology. The unnuclear physics here is a play of words. It's a non-relativistic version of what Georgi called unparticle physics. And unlike unparticle physics, I'm going to argue that in fact there are real nuclear reactions where we can apply the formalism of unnuclear physics and obtain interesting results. That would be difficult to explain to obtain otherwise. So the plan of my talk is to first review Georgi's unparticle, and then talked about the non-relativistic conformal field theory, following basically the paper that Yusuke Nishida and I wrote some years ago. And then we are going to discuss applications in reactions, nuclear reactions of this formalism. Okay, so what is an unparticle? So in 2007, Georgi asked the following question. Suppose, so all we know in the standard model are particles. These are fields whose propagators have a pole. He asked, what would happen if we have in nature a field that whose propagator is not a pole, doesn't have a pole but a cut? And an example of such an object in field theories is a field in a interacting conformal field theory. So in conformal field theories, if we have a field U, its propagator will, in real space, will have a form of a power law behavior, 1 over x to a power. When this power is is twice the scaling dimension of the operator U. So you see here, first it falls off at infinity is like a power law, it's not like an exponential, as the case of a massive field. And if one fully transform this to the momentum space, then we will see a propagator that has a power law form as a function of p, where this power might be fractional. It's 2 delta minus 4. Delta is the dimension of that operator. In fact, this formula is valid only if, well, strictly speaking, only if this is not an integer. If there is, if it's an integer, there might be a additional logarithm in this formula. Except the case when this particle, this field U, is a field in a free field in a massless field theory. For example, a massless scalar field theory. Then this delta would be equal to 1. the dimension of this operator is just naive dimension. And the propagator, of course, would be 1 over p squared. But otherwise, for any other dimension different from 1, the propagator doesn't have poles. It will have a cut from 0 to infinity. And so an example of such a unparticle or a field in a conformal field theory is the simplest case would be just take the massless scalar field and take the operator to be phi to the n power. Then the propagator of phi to the n would be the nth power of the propagator of phi in coordinate space. Another more sophisticated example of such an unparticle would be the so-called Banzak's fixed point in gauge theory with fermions in the fundamental representation. Say if I have usual number of colors as in QCD, NC equal to 3, but the number of fermions is say close to 16, the theory would still be asymptotically free, but there is no confinement. The theory flows to a fixed point with finite gauge coupling, and the physics here would be completely different from what we are used to in QCD. There are no particles, but there are only these unparticles or fields with power law correlation function. So when I think about this unparticle, I have in mind something that doesn't propagate with as a particle. It's a fuzzy object corresponding to a cut in the propagator. Now, one can ask what would happen if we have such a sector interacting with particle in the standard model, and that is what Georgi asked in his pair of papers in 2007. Imagine that we have some collisions, 2 particles in the standard model that give rise to another particle, let me call that B, but then we have unparticle U. So in the detector, what we would see is missing energy. Suppose we cannot detect this unparticle U's, then we detect this particle B. The spectrum of B would be will be continuous unless U is a particle. Say if A and A1 and A2 are say electron positron, give rise to B and an unparticles, then the spectrum of B should be continuous. That's because again the propagator of U doesn't have a pole. It's not a particle, but its energy it can have all kinds of energy with a given momentum. Another way to see that the spectrum of B should be continuous is to take the simple example where U is nth power of a scalar field phi. And in this case, the reaction looks like A1 plus A2 goes to B plus n of the scalars, right? And since if n is larger than 1, then kinematics would tell us that the spectrum of B is continuous. Now, the spectrum of B is continuous, but there are still, we can still ask various questions. One interesting question for the purpose for later in the talk is to ask about the behavior of the differential cross-section as a function of the energy of B when this energy, this B energy of B is close to the maximum possible energy. So let's imagine, so let's draw a graph here. So we would measure d sigma over dE, where E here is the energy of the B particle. So obviously it will have some form like this. And from this argument, from this example, it's clear that the behavior of the cross section near the endpoint here. So here is E. Near the endpoint would be dependent on how big is N. Basically, the behavior the sigma over the EB is dependent on the phase space of the N final state phi particles. And it turned out that this conclusion roughly remains valid when N is fractional, or we are dealing with a general field in a conformal field theory. So Georgi analysis show that the behavior of the cross section when we have here some operator U in the conformal field theory would be exactly the same as if we have delta massless additional massless particles in the final state. Okay, so is there any questions so far? Okay, if not, I'm going to leave the relativistic words and
excuse me.
Yeah,
I have a quick question.
Yes,
sorry,
sure.
Can you hear me?
Yeah, I can hear you.
Thanks. So first, in the condensed matter, we have this 2-point correlation function. Like at critical point, you have this delta x to the sum minus delta sum exponents.
Yeah.
What's the relationship to those correlation functions like susceptibility, etc. in the condensed matter? They also are, I mean, those are not, those fields are not particle fields. And they also have this correlation function. So is there a relationship?
Yes, there are critical points in condensed matter physics, in particular those with so-called Z equal to 1, dynamical critical exponents that are exactly governed by the conformal field theory. In this case, usually in 2+1 dimension rather than in 3+1 dimension. So the physics near this point are exactly the same. The precise question that we are asking here about the behavior of the cross section is not an usual question that one would ask in condensed matter physics, but I think in principle this question might be asked as well.
Okay, thanks. And second question, if we consider just some massless particles like a neutrino in standard model, we also have, I mean, it's massless, so in classical sense, of course, does it have a behavior like this unparticle? But it's a particle, right?
Photons, for example, would be a massless particle, but it's not an unparticle in the sense we are discussing here. The more formal level, the propagator of a photon field or neutrino, for that matter, has a pole. That means that if I fix the momentum of this particle, its energy has to be fixed. While for the unparticle, if we fix this momentum, there is still a distribution of energy that this object can have. So masslessness doesn't mean that, doesn't imply that it's unparticle. We need to have dimension different from that of a free field.
Okay, so it's determined by this propagator. Okay.
Yeah. And the form of the propagator, we will see later one example of a propagator that doesn't have the usual form of a particle, but in the non-relativistic framework.
Okay.
So, yes. So quantum mechanics of many particle system is basically a field theory. of a particular type. If one write down quantum mechanics in the second quantized formulation, like here, what I did here, we would have an action of a non-relativistic field psi, which can be either fermion or bosonic field. The kinetic terms of this psi field has a non-relativistic form in which the time derivative appears as a first order and the spatial derivative as second order. The interaction in quantum mechanics is governed by, say, some potential. Usually, when we solve a quantum mechanical problem, we fix this potential. So this Lagrangian looks a bit not very nice due to the presence of non-local interaction here. On the other hand, in some example that we will consider later, the interaction can be thought of as a local interaction, basically a delta functional interaction, which still leads to non-trivial physics. Now, this theory that we have written here has, for all possible potential, certain symmetries, space and time translation, and Galilean invariance. In one particular case, in some cases, one of which is a trivial case when the potential is equal to 0, the theory has some extra symmetries. If we have only the kinetic terms, we see that the theory has scale invariance, under which the spatial coordinate transform twice slower than the temporal coordinate. So if we replace x by lambda x, t by lambda square t, and psi by lambda to some power minus delta psi, the action is invariant, but this delta is going to be the dimension of operator psi. For a free field, this delta is equal to d over 2, where d is the number of spatial dimensions. So 3 over 2, 3½ for theory in 3D, 3 plus 1D, if we include the time direction. However, this is not the only additional symmetry that we have for a free theory. The full group of symmetry of the action, of the free action, is the so-called Schrödinger symmetry. It's a symmetry of the Schrödinger equation. So that's why it's called Schrödinger symmetry. And we can take t goes to 1 over 1 plus some constant time t in transforming x the same way. And we can check that, one can check, I'm not going to write down the formula here, that there is compensating transformation of psi to make the action invariant. So this is called the proper conformal transformation. There is only one one additional proper conformal transformation in the Schrödinger symmetry group. Another way to discuss the symmetry is to give the algebra and the commutators of the generators of the algebra. So here on this slide, I list all the operators written in terms of the creation and annihilation operator of psi. So we have spatial translation, and time translation can be also written in terms of psi. The Galilean boost turn out to have this this form. Dilatation and proper conformal transformations are all can be written in terms of this operator psi this here. So the proper conformal transformation, you see, it looks exactly like a moment of inertia of our system. It's integral of x squared times psi decker psi, which is the density. The angular momentum and the mass are the only remaining operator. And by using there's various ways one can compute the commutator between these operators. One way is just to use the standard canonical transformation of psi, canonical commutation relation of psi, and we get a certain table that give us the full algebra, the Schrödinger algebra. I'm not going to go into detail of these, except for to comment on certain aspects of this Schrödinger algebra. So first of all, there is an operator, the dilatation, D. The commutator of the dilatation with an operator is determined by give us the dimension of that operator, delta. So for example, if I commute delta, I'm sorry, this one should be should be the dilatation, D with O. Okay. If I commute D with H, I have 2IH. So the dimension of the Hamiltonian is 2 and the momentum is 1. Like E is equal to P squared. And so the dimension of energy is 2 and momentum is 1. While the dimension of this Galilean boost is -1, and of this proper conformal transformation is -2. Another fact also interesting is that this H, C, and D form SO 2,1 subalgebra. It's actually an important fact that I'm not going to use this explicitly in this talk, though. If we have a field theory, we can classify operator based on its properties. So two of the properties. One is mass of the operator. In a field theory, non-relativistic field theory, we can have the single particle operator has mass m, and say psi would have mass 2m. And an operator can also have a dimension. So we also know from what has been discussed before, commuting the operator with P and H increases the dimension of the operator by 1 and 2. It's very easy to understand. P is, well, one way is to use this commutation relation. Another way is to think about P as spatial derivative, and this is time derivative. Time derivative increases the dimension of operator by 2. But commuting an operator with K and C reduces the dimension by 1 or 2. And using these facts, we can build a representation of operator. This representation theory is can be it's rather simple for operator with mass not equal to 0. Roughly speaking, operators are organized in towers raised by a pair of operators P and H. So if I have an operator with dimension delta and I act derivative or commute the operator with momentum, I get a new operator dimension delta plus 1. I can commute with P another time, or commute with H and I get an operator with dimension delta plus 2. And if I commute the operator with K or C, I lower the dimension by delta to -1, -2. And there is a limit on the dimension of operator. There is a unitarity limit, and that means that I cannot lower the dimension of operator up infinitum. That is, there is a set of operator which can be called primary operator, for which one cannot lower the dimension further. So that's the definition of the so-called primary operators. So in a free field theory, an example of a primary operator is, for example, psi. An example of a higher of another free field operator that is an operator in free field theory that is primary would be something like this. Minus, suppose let's assume that the field is fermionic. You can write some operator like this, but the total derivative of, say, psi down is not primary. Is can be not it's not a primary operator, and all that one can check by just taking this operator and commute with k and c and see whether it gives us a 0 or non-zero value. One very important, very nice and important for our intuition statement is the operator state correspondence in non-relativistic conformal field theory. In the usual relativistic CFT, there is a correspondence between the dimension of an operator and the energy of a state on a sphere. While in the non-relativistic CFT, the equivalent statement is the equality between the dimension of an operator, a primary operator, and the energy of a state in a harmonic potential. So one very simple example of such a correspondence is a single particle operator in free field theory. Psi has dimension d/2, but if I have a ground state, I can ask about the ground state of a single particle in a d-dimensional harmonic potential, and I see that this energy is d/2 times h bar over omega. And this statement tells us that this number, the fact that these two numbers are the same, are actually not accidental. The dimension of operator is always equal to the dimension of a state in a harmonic potential. We will see another example of such a correspondence in a more non-trivial setting of interacting field theory. But all this, yeah.
Sorry, can I ask one question?
Yes.
Yeah, is there some more fundamental way to see this operator state correspondence in this theory, similar as we do it in relativistic CFT?
Yes, so to prove that statement, one use the following things. We can use the we use the SO2,1 subalgebra formed by D dilatation Hamiltonian and the special conformal transformation, and the way to construct such a, so with any operator O, say an operator like psi, right? I can act on the vacuum. So it takes O at point 0, acts on the vacuum. I have a state that is basically a delta function, a wave function near the vacuum. And then I evolve that state using the Hamiltonian under time, Euclidean time equal to 1. And that turned out to be an eigenstate. One can show that it is an eigenstate of the new Hamiltonian H plus C. Psi is equal delta of O of psi. And so this is a very general proof. H of C, of course, is the Hamiltonian of a system in a harmonic potential, since C is it's like x square integral of x square side equals psi. And so 1/2. And so that's has a little bit of this. It has a. It's very general, and so one can base only on the algebra.
Thank you. Thank you.
Can I ask a question too?
Yeah, sure.
Two questions. So is H plus C here like the conformal Hamiltonian in relativistic systems, P0 plus K0?
I think so. Yeah.
Okay.
It's now.
And then we're gonna allow the spectrum to be continuous for the operators as well, their scaling dimensions, or no?
The spectrum will typically be for a given theory will be not continuous, will be discrete.
Or sorry, I mean the allowed set of deltas.
The allowed set of delta. I know that in two dimension, almost we can write out a theory with any dimension we want. It's anyons. We'll just write a theory of anyons and can mimic operator with any dimension. In 3D, 3+1, the number of example is a bit restricted, but the spectrum can be changed continuously. But I don't know if there is any. There is no. I don't have an intuition of what are the allowed value.
All I'm asking is because a harmonic potential just has quantized energy states. So are you saying that I can think of it as varying omega to get to any energy state I want?
No. It has to be the following. It has to. We fix this omega to be 1 here, and then ask the question: if we have particle here, and can we change the interaction between these particles? So you have a few particles. We change the interaction between these few particles so that this energy can change continuously.
Okay, thank you.
Yeah,
thank you.
Yeah, I think it's in a certain in a finite range one can do it in any dimension. But let's push forward more formal formalism independent of the theory. If I have a primary operator in a non-relativistic conformal field theory, one can show that the two-point function is completely defined, is completely fixed by the mass and the dimension of this operator, delta. So the form of the propagator is written here. It's if delta is equal to the dimension, if delta is equal to d/2, this is simply the propagator of a single particle written in coordinate space. If I Fourier transform this to momentum space, you'll see that up to a contact term, the green function looks like a power of p squared over 2m, where m is the dimension of that is the mass of this operator, minus omega to the power of delta minus 5/2. If delta is equal to 3/2, this is against the propagator of a free particle. But if delta is not equal to 3/2, then it's basically a propagator with a cut instead of a pole. Including the case with delta equal a half integer larger than 3/2. Actually, in these cases, there is an additional logarithm in the propagator that I didn't write here. Now, this quantity omega over is this quantity omega minus p squared over 2m is the energy of our object in the center of mass frame. If I do a Galilean boost to the frame in which the total momentum carried by u is equal to 0, then its energy should be equal to omega minus p squared over 2m. So this expression is Galilean invariant. Actually, Galilean invariant fixes and scale invariant fixes this form. Now, for a 3-point function or equivalently the coefficient in the OPE of product of two operator, the situation in non-relativistic conformal field theory is more ugly than in the usual conformal field theory, relativistic conformal field theory. So we have the usual 1/x factor fixed by the dimension of the operator participating in the OPE. But we also, in this case, the coefficient turn out to be a function, in general, a function of x squared over t, which cannot be further determined based on symmetry alone, except in one case, except in the case when one of these operators is a free field, then this coefficient can be determined from the dimension of the operator. So we will not use this. I thought it's a curious fact, maybe a little bit less known in relativistic conformal field theory. We are going to need in our further discussion only the 2-point function. Okay. Okay, so let me give one example. This is going to be a first non-trivial example, and probably the only non-trivial example of a interacting conformal non-relativistic conformal field theory that we are going to need. So the theory here is known in the literature as the theory of fermions at unitarity. Mathematically, it's the following system. We have the non-trivial modification compared to the free theory is in the Hilbert space. So the Hilbert space is given by a state with wave function. So here I'm assuming particles are spin 1/2 particles, fermions, and the wave function is a function of the coordinates of x and y, where xi's are the coordinates of spin up particle and yj's are coordinate of spin down particle. So I can have any number of spin up and spin down particles. And the requirement on the wave function when I go to yj, that is when I take one spin up particle and one spin down particle and take their coordinate to be close to each other, is that the wave function has to have a particular form of singularity and singular behavior near this point. Basically, it has to be 1 divided by x minus y without a constant term. We know that it's allowed because Laplacian of 1/r is basically 0 if r is not equal to 0, and so this satisfies the basic requirement that the kinetic energy of this object does not blow up due to the singularity, and also this asymptotics is consistent with normalizability of the wave function. The integral of psi square is not going to diverge due to the 1/r behavior asymptotic. So we have a completely well-defined quantum mechanics given by this this condition on the Hilbert space and the usual Hamiltonian, which is just the sum of the kinetic energy of all particles. And we can do all kind of quantum mechanical problems with this Hamiltonian. So for example, one can ask, suppose I have two particles in a harmonic potential, one spin up and one particle is spin down, but with this particular restriction on the wave function, condition on the wave function, what would be the ground state? And you see that the ground state wave function actually can be found exactly. It has the form shown here. The numerator is the wave function one would have if the boundary condition at x equal to y is usual, the non-singular, then we would have this wave function. But here we have some kind of, effectively these two particles attract each other, and so the wave function goes up at x goes to y, and so the energy of this object, these two particles in harmonic graph, is also less than the value it would have in a free theory. So it's E equal to 2. So here we have an example of a theory with an operator with mass equal to m and the dimension equal to 2. This is a interacting field theory. One can formalize it in a more, one can write this theory in a slightly more familiar form. This is the Lagrangian we start with, particle, free kinetic terms, and then a delta functional local interaction. This local interaction then we can write using an auxiliary field phi in this form, and then this phi is going to be the operator that has non-trivial dimension in our case. So let's compute the propagator of this auxiliary field phi. So in this case, this phi is an object that decays into two, one spin up and one spin down particles, and its inverse propagator is just the bare inverse propagator plus this one loop integral. So now in this free non-relativistic theory, this one loop approximation is exact, and when we compute this one loop integral, we find it's divergent, linearly divergent. There is a linear divergent piece proportional to the cutoff, and there is a finite piece. And what we are doing here to arrive to a theory called fermion at unitarity is to fine-tune the bare coupling to cancel out the UV divergence of this one loop graph. So this sum is equal to 0. In the language of quantum mechanics, that corresponds to taking the S-wave scattering length A to infinity. More physically, we can think about the process of this fine-tuning as fine-tuning the depth of the potential, so that there is one single bound state at threshold equal to 0. And
so in your cancellation, that's C naught inverse, is it?
C naught inverse, yeah. C naught inverse. Sorry. Yeah.
Oh yeah. Okay.
Thank you. It's also inverse here. And yeah, so the propagator of this field phi is now going to be just equal to 1 over square root of omega minus p square over 4m, p square over 4m minus omega. So that's very typical of a propagator of a field, non-free field theory, field in conformal field theory. For fermion at unitarity, one can go further, and just going to show you the result here. The dimension of operators that one can construct from more psi, like 3-body, 4-body operator, can be computed either using this the field theory. Usually one has to supplement it with some approximation like epsilon expansion, or a direct quantum mechanical calculation in a harmonic trap. And one gets this dimension of operators. So these two we have, these two is exact, we know. This dimension of the spin 3 operator, one with angular momentum 1, the other angular momentum 0, are also non-trivial, but basically they are known exactly. I'm just giving the approximate formula here. It's some solution to some transcendental equation. And for 4 particle and above, we only have numerical result, for example, by Monte Carlo simulation of, say, 4 particle in a harmonic potential. Okay, so let me now try to see what we can, what one can use this non-conformal field theory for in the real world. In the real world, there are some systems where accidentally the scattering length, the system is almost fine-tuned to infinite scattering length, or to almost a bound state, a threshold. So some examples are given here, but I'm going to just concentrate on the last example, neutrons. So neutrons, we know neutrons have a very large scattering length in S wave, minus 19 Fermi. So minus means that the neutron do not form a bound state. They almost form a bound state. This is much larger than the typical length scale of nuclear force, which can be measured, for example, by the next term in the effective range expansion called the effective range, R0, about 2.8 Fermi. In the idealized regime, when the scattering length is infinite and the R0 is equal to 0, we would go back to this theory of fermions at unitarity that have been presented in the previous transparencies. And that means that in some regime of length scale between these two length scale, the physics of neutrons is governed by this conformal field theory of fermions at unitarity. So
excuse me. So
yeah,
the R not correspond to which quantity in the field of theoretical description? Or do you have
it corresponds to operator which has two more derivatives. It's for fermion interaction with two spatial derivatives.
I see.
Yeah. And so suppose suppose we look at some nuclear reaction with while neutrons are produced in the final state. So some of these are listed here. If these final state neutrons can be in some, which we will argue in some regime, can be thought of as an object that do not form a nucleus, but can be thought of as forming an unnucleus, or they can be described by a field in a non-relativistic conformal field theory. And for that approximation to be applicable, the kinetic energy of these neutrons in the final state in their center of mass frame, center of the frame of the center of mass of this neutron has to be between these two numbers governed by the scattering length and the effective range. So it's between 0.1 and about 5 MeV, almost 2 decades in energy. In this regime, this object form a non-relativistic version of Georgi's unparticle that we would call an unnucleus, since nuclear physics is basically particle physics at the in the non-relativistic regime. Okay, so here is what the idea is. Suppose we now have a reaction where we take two initial state particles, collide them together. They form one single nucleus, say, or
sorry, before you start this, could I ask you a question about the previous slide?
Yeah, sure.
So are you setting up here something where the corrections to your unnuclear picture are given in powers of R0 over A, or is it powers of R0 divided by other scales and other scales divided by A?
There is 3 scale in this problem. So there is an energy scale or the momentum scale. Let's call that the momentum scale, or the energy k square over 2m or m neutron. This is the energy of the neutron in their center of mass frame. So with these neutrons here, relatively they move with momentum k, and there is R0 and there is A. So the expansion parameter should be, so when k let me assume a regime K much larger than 1 over A, much smaller than 1 over, much larger than 1 over R naught, 1 over A, then the correction, there is correction that is proportional to K R naught in principle. That has to be much larger than, much smaller than 1. There is KA that I'm also going to assume that's to be much smaller than 1. But I'm going to argue that KA correction can, in principle, be resummed.
Okay, thank you.
Yeah, but suppose I have a reaction where I have two particles colliding and producing a particle and a number of neutrons. So the energy.
Son, can I interrupt you a second?
Sure.
Sorry, can you go back one slide? I'm a little confused about dimensionality. So A is supposed to be the scattering length.
Yeah.
So
like this 20 Fermi.
Exactly. So you want it to be very big. So you want K to be much bigger than 1 over A, probably, or not?
No. K is much bigger than yeah. Sorry, A.
And K much more than 1 over naught.
Yeah, this one is a bit yeah. K has to be smaller than R naught. But
so you want Ka to be much bigger than 1.
Ka much bigger than 1, but this 1 over Ka I think can be resummed.
Yeah. Okay.
We haven't done that in more interesting cases, but in principle it should be done. So we want to consider this reaction. The spectrum of the energy spectrum of B particle, of course, will be continuous, and so we ask about the differential cross section as E sigma over dB. So here E and EB I'm going to denote the same quantity. So it will have some behavior, and then has a cutoff at some maximal values. If we are if the energy of the B particle is near the maximum, then from kinematic calculation we can see that the energy of the neutrons, the neutron will move almost with the same velocity, with the same momentum, and their relative momentum is small. So in this regime, we can think about the reaction as proceeding in 2 steps. In the first step, we produce let's call that the primary reaction. In the primary reaction, we produce particle B's and a lot of neutrons. And in the later stage of the reaction, this neutron move, but they keep interacting with each other because their scattering length is so large. They have to move further than 20 Fermi to stop interacting. And so we can expect that there is a factorization of the total rate into 2 parts. One is the primary rate of primary reaction. So here I have this factor, basically the phase space of the particle B. But then I have also the later part. This is the cell interaction between these neutrons, parameterized by the imaginary part of this unparticle field U. So the idea here is that we can think about this reaction as effectively we have some reaction where we have particle B and then some kind of unparticle U, and the square of this rate is this diagram. And when I cut this diagram here, I would get the imaginary part of the green function of the unparticle U. So that means I can use conformal field theory, non-relativistic conformal field theory to investigate the rate of this reaction near the endpoint of the spectrum of B. So doing the calculation, we see that this green function, basically the argument of this propagator is equal to the distance of the energy from the endpoint. Right? So just simple kinematics, or we can do that in calculation. What is the argument of the green function? So we see that near the endpoint, the differential cross section has to behave like E0 minus E to the power, and the power is the dimension of this unparticle U in the non-relativistic field theory. Any question? So that means that we can predict, for example, what would happen in these nuclear reactions. So here it should be sigma. The prediction is that the behavior of, for example, a 3-particle reaction like the medium one, middle one here, has a power which is some irrational number. Of course, we have only a finite range in the energy of n, and so we can only determine experimentally this number up to some accuracy. But it's almost it's more than 1 decade in energy, so we should be able to see that in real data if we can measure it. And so we haven't found the data that zoom into this endpoint with a good enough accuracy to compare with our prediction. But there are theoretical calculations based on nuclear, just straightforward nuclear potential and some assumption about hadronic reactions. So, for example, there is a theoretical calculation of the rate of the process in which a helium-3 nucleus absorbs a pi minus and emits a gamma and becomes 3 neutrons afterwards. If we look at the result of that theoretical calculations based on nuclear potential, we see that the data they fall into this power law in a quite nice way. They start to deviate at about 2.5 MeV. So they start to deviate more if we go to higher energy. But for low energy point, we see the curve goes through the point quite nicely. The same is for another reaction in which the helium absorbs a mu minus and emits a muon neutrino, becoming 3 neutrons. Again, this data, it's almost the same reaction as this one, except that here we have weak interaction instead of a strong interaction.
Sorry, I'm trying to understand how the charges work there. Is it tritium or helium-3 that you've got going?
Oh, I'm sorry, this is tritium, not helium-3. Sorry, tritium.
Okay, but I'm thinking that, so then if it's tritium, then you've got a charge 3 plus
proton, neutron.
I'm sorry, I got it. Okay, I'm with you. All right, thank you. Thanks.
Yeah, I got confused about simplest nuclei as well. But yeah, but there are comparing these, it's we see that the prediction borne out almost perfectly. The deviation from the power law scaling starts around 2.5 MeV. it's around the same value as we expect, is 5 MeV. Maybe here we see an effect that this nucleus, the helium, the tritium nucleus is not as tightly bound as, let's say, helium-4, and so the factorization may work a little bit less perfectly than, say, with a more standard nucleus. Okay, so my time runs out. Let me go to the conclusion. By viewing the final state neutrons as forming an unparticle, one can predict power law behavior of the differential cross-section near the end point. More detailed calculation should allow us to zoom in into an even smaller energy region, about 0.1 MeV. Basically, there we have, if the energy of these neutrons are less than 0.1 MeV, they are further away than 20 Fermi, and so they should have like free particles. So the crossover to free particle from unitary fermion to free particle is described by a renormalization group flow from unitary fermion to free fermions, and that in principle should be treatable. And it would be interesting to see if there are unparticle or unnuclear behavior in other non-relativistic systems. Say, one example is nuclear reaction with production of 2 alpha nucleus, but I leave that to future work. Thank you very much for your attention.